right. So let's work on the following problem first. This is the integral, triple integral, and E is determined by root 2 in coordinates. All right. So first of all, you have to draw the graph, right? Sketch the graph and to understand the region E. X squared plus y squared is less than or equal to 1. That means it's going to be a cylinder in 3-dimensional space. Then z is between 0 and x squared plus y squared. So you have to understand the surface z equals x squared plus y squared. Z equals x squared plus y squared is paraboloid. Okay, and the z is between this z equals 0 is a xy plane. So that means this is the part we're talking about. Right, this is solid. Right, under that. Okay. Right. So the best way, well, you don't need to use a cylindrical coordinates to solve this problem. Okay, so if you did not describe this one by d, you have a triple integral, right? Triple integral can be changed to a double integral, right? So double integral is dA, and inside for each point, for each point x and y in D, right? D is a disk determined by x squared plus y squared less than or equal to 1. Okay. So for each point x, y was called x, y. You find you draw the vertical lines. Those vertical lines occupy the solid. Okay. So this is a iterative integral, but I don't write down all the 3 single integrals directly. So you will get, okay, this is a dz, here's z, right? And z is between 0 and x squared plus y squared, right? Yeah, the lowest value for z is going to be 0. The highest value for the z is going to be, the largest value for z is going to be x squared plus y squared. Right, so then you evaluate this integral, you will get half of z squared and x squared plus y squared dA. Okay, so you will get in x squared plus y squared and dA. Okay, and it's squared. So now you're going to have you have a double integral on the disk. So double integral on the disk. Since the disk, it's disk, so the best way to evaluate this integral is to use the polar coordinate. So-called polar coordinate is just the substitution. Okay, so this is the disk D, but we also have R and the theta, right? R is between 0 and 1, theta is between 0 and 2 pi, and you have a rectangle, and this rectangle map to here. Okay, this is a picture. So the map is determined by this. Okay. According to, yeah, that's dA is here. Okay, according to this is called a d bar. Okay, according to the formula, this integral becomes the double integral on d bar, and half of x squared plus y squared is r squared, then square, right? But don't forget there is a derivative of this map. Determine the derivative of this map. It's actually the r and dA bar. Okay. Yeah, this comes from the, don't miss that part. Okay, comes from the derivative of this is kind of a 2-dimensional function. Okay, roughly speaking. So you will get a the double integral over this rectangle. If it's a rectangle, you can always write it like, use the Frobenius theorem, right? It's easy. All right, half of r to the fifth dr and d theta. Doesn't matter which order. Then the antiderivative of this, it's 2 pi, okay? Anyway, it's constant. So antiderivative of this function will be 1 over 2 times 6 will be 12 r to the 6 function. So the answer will be pi over 6. Did you get that? Okay, so this is the idea. we turn the triple integral into a double integral, into iterative integrals. By iterating, only 2 integrals here. Okay, one is double integral, other one is a single integral. Okay, step by step, we don't break the triple integral into 3 single integrals. Okay, because it's sometimes it's impossible. There was a disk there, right? It's a cylinder. It's a cylinder. Now, of course, you can use cylindric coordinates for this triple integral. Okay, you can do that, no problem. If you use it's the same result essentially. Yeah, it's the same idea. Okay. What we're going to do today is going to be introduce another type of map. Okay, its typical example is a domain E is going to be a sphere or a portion of the sphere. For example, yeah, consider a triple integral fxy z and dv, and here E is going to be the sphere, right? The ball, yeah, it's 3-dimensional. Then we it's harder to turn this to the iterative integrals, right? How to evaluate this triple integral. So the idea is this is a ball, okay, inside. So this is 3-dimensional space. Yeah, let's look at the example first. This special one. So how can I use substitution, okay, or use a new coordinates to turn this triple integral over ball into a triple integral over a rectangular box, right? Then you can easily apply the Fibonacci theorem. So the map, we do have a map here, okay? And I'm going to draw what's the notation for the, yeah, let's call this is R, this is a theta, this is a phi, okay? So you can have a box, okay? This is going to be rectangular box. It's a sphere is going to be the image of the box, surprised, right? How do you describe that? Okay, this is that's called phi. Okay, so there's a formula here in this book. They're going to use a row. Okay, so this is a row instead of a thing. Okay, so how do I do that? This is a map. Okay, x equals rho sine phi cosine theta. Y equals rho sine phi sine theta, and z equals rho cosine phi. Now, how do we understand this? Okay, this is what we do. You take an arbitrary point inside the ball. It's coordinates x, y, z. What I'm going to do is I'm going to draw this line from the origin to that point, and project it to the xy plane. So you get another point. The length, the radius, okay, of that point in the xy plane. Let's imagine this is here, okay? So that is the point here. So this will be R. And then you have angle theta. And this is theta, okay? This is theta. And this is the angle is a phi, okay? So phi is between 0 and yeah. So the length between the origin that point is rho. Okay. Then you will see that I is going to be rho low sine phi. Okay. How do I see that? I is going to be low of a sine phi is because it's in three-dimensional space. I is low of the sine phi means you're going to prime the sine value. You see, sine phi times the other side of the right triangle, you can measure the length of this red line. Okay, so this is R. Then this is actually the length between the origin and the point, which is a projection of the point XYZ in the XY plane. So you get this. Then, okay, this is going to be X, right? And the Y, no Z here. So X is going to be R cosine theta, and Y equals R sine theta. So if you replace R by low sine phi, then you can get, you can solve the problem. So here Z is going to be rho cosine phi, okay? Because the cosine value times rho is going to be tells you the height of that point in the space. Okay, so this R can be replaced by this, then you get that above map. Okay, I'm trying to understand the map. All right, so now you have a three-dimensional substitution, okay, which sends this will be pi in this particular case, pi, and this will be 2 pi, and this is a capital R, okay? So this is a box, okay? Low is between 0 and the capital R, and the theta is between 0 and the 2 pi because you rotate around the ball, right? And then phi is only between 0 and pi because from north pole to the south pole, okay? So that's slight different. All right, so now this, I'm going to call this one E bar, okay? And the volume for element is dV bar, okay? Here, this is a E, and the volume development is dV, okay? So the triple integral of over E fxyz dV becomes a triple integral over E bar, which is nice. It's a box, right? And here still fxyz. I'm not going to replace it too much there. Where xyz will be replaced by above formula. Okay. Okay. And what I have here is the additional part is going to be the determinant of xyz with respect to rho theta phi. Okay, and then dV bar. Okay, and what does that mean? This is a derivative of the map. Okay, and the derivative of the map is a determinant of this matrix. Okay, the determinant of this matrix after we compute it, we find out this part. Okay, I'm not going to waste time to do the calculation. This part is going to be the rho square sine phi. Yeah, after you do the computation. Okay, so this is the determinant of the matrix, absolute value of the determinant of the matrix. Okay, and that's it. So this is a formula very similar to the this is three-dimensional substitution. Okay, but the good part is this substitution changes the domain, a very bad domain to a nice domain. Okay, so the picture is as above. Okay. Sphere, I found the so-called spherical coordinates. It give you the map, which sends the box to rectangular box to the sphere. Of course, there's some face of the box will collapse to the point. Okay, but that's just a one face. It's okay. Most of them, it's just one-to-one map. Okay, it does not change. Yeah, change it too much. So nice map. Mapping is very important. It's harder to construct actually. Okay. But this is a very good example. Now we're going to look at some problem. Now in the for the real problem, it's not the domain. The region E is not the whole sphere. Sometimes like half semi-sphere. Okay. Then you have to determine the corresponding E bar. Okay, it could be portion of this rectangular box. Okay. So let's do some exercise first to understand the map. Okay. This is a coordinate map. So we are going to determine, changing. The first problem I'm going to do is changing from rectangular to spherical coordinates. Okay. Okay. So here's the point. Square root 3, -1, 2, square root 3. So this is a point in the x, y, z space. Okay, space was coordinates x, y, z. Okay, so we are, so you are here, okay, somewhere here, and you want to find the corresponding point in this rho theta phi space. Okay. So think about this, right? So what to get here is actually, I should say that rho square is going to be x squared plus y squared plus z squared, because I forgot to mention that this is for this map you have this identity. Okay, so you can determine what I want to do is I want to change to some point here rho theta phi. Okay, I have to determine rho theta phi. In other words, you're going to solve, find, you have to find out things like that, okay? Using x, x is going to be rho sine phi cosine theta, right? Y equals rho sine phi sine theta, and z equals rho cosine phi, right? And for a given given this, find rho theta phi. Okay, in other words, right? And using the above formula, so you're going to find the pre-image of that point in for this map, right? So there's a map here. But step one, I have to find the rho. Rho is positive, right? Rho is going to be x squared plus y squared plus z squared, so it's square, -1 square, plus 2 square, 3 square. Okay. Yeah, we can determine that. So 3 plus 1 and 12. So 12 power 4 is 16. So rho is going to be 4. Okay, great. Guys, this is actually the point on the sphere with radius equal to 4. Yeah, 4. So you can even draw the sphere here. Somewhere here. Okay. So this is rho equals 4. Okay. So how can I determine the theta? And how can I determine? I think I can determine the theta first. Okay, since you already have the x coordinates, right? Yeah. So this is a theta. This is a phi. Okay. So the x coordinates. X coordinates is going to be square 3, right? So actually it's going to be rho cosine theta. Y equals r equals sine theta. Right? Right? Here r is going to be, we don't know yet. R is going to be rho sine phi, but we don't know yet. Okay? If I can determine r, then I can determine phi, right? So this is going to be square 3. That's going to be -1, right? It's not changing. So from here, I can determine r. Okay? R is going to be, r squared is going to be x squared plus y squared. Okay. Okay. So r squared equals x squared plus y square, which is 3 plus 1, that's 4. I is going to be 2. Okay. Great. So immediately I can get, then I can get cosine theta equals square 3 over 2. Sine theta equals negative 1 over 2. Okay, where theta is between 0 and 2 pi. What is that angle? That angle must be in the fourth quadrant. That angle must be in the first quadrant because sine is negative, cosine is positive. Okay. So reference angle is going to be 30 degrees. Okay. So this is theta. This is a reference. Do you remember, right? The sine of the reference angle is going to be the absolute value of sine theta equals 1/2. Then the reference must be pi over 6. Right? Yeah, the so-called reference angle is the angle between 0 and pi over 2, and its value is going to be absolute value of the corresponding trigonometric function, value of the trigonometric function. Right? So then you can see that theta A is going to be 2 pi minus the reference angle, 2 pi minus pi over 6, which is going to be 12 at 11 pi over 6. Okay, so you determine the theta. Oops. Anything wrong? Oh, what's this? Okay. So you get a theta. Now, how do you get a phi? Remember, we call the phi, right? I equals rho sine phi. So I is going to be I is going to be is 2. Rho is going to be 4. Sine phi. So that means sine phi is going to be 1/2, and clearly phi is going to be pi over 6. Right. So we find the spherical coordinates, which is going to be 4. Theta is 11 pi over 6, and then pi over 6. Okay. So step by step, and you can get the pre-image of that point. Yeah, let's go back to this picture. Right. Yeah. We find a point here, which is rho is going to be 4, and the theta is going to be pi over. Yeah, this is 11 pi over 6. Here's a 4. What is rho? Well, I forgot to find. Rho is 4. Yeah, phi is going to be pi over 6. So this is a pi over 6. How can I draw pi over 6? It's harder to draw it. Okay. This is going to be like that. Yeah, must draw a parallelogram. Okay? Pi over 6. Then it's like in the space. Yeah. Yeah. So this is a point was ascended to that point. Right. On the sphere with radius equal 4. If you don't want to draw the graph, that's fine. And you needed to determine step by step, determine the rho, right? If you're given the x, y, z coordinates of the point, you determine the rho. Okay, then you determine the rho, then you have to determine theta. Once you determine the theta, you can determine the phi. Okay, step by step. But we are going to work on the spherical coordinates. Right, the first problem I want to discuss is most of the time, maybe I just want to set up integrals. Right, it's going to be the problem number 22, for example. Yeah, number 22. We consider this triple integral. It's y square z square and the dv. Okay, E lines above. Oops. Above the cone, we are told that this is a cone. Now, phi, oh, this is already described in the sphere coordinates, and below the sphere, rho equals 1. Now, what does that mean? Okay, so funny here. This is an integral in the XYZ coordinate system because the variables here y, z. But the region is described by as the image of the as the image of some region. Okay, so let's describe this. Okay, so this is I don't have a picture here, but I do have a I have a rho, I have a theta, I have a phi. Okay. Actually, E is the image of another region. Okay, so let's describe the E bar first. So what does that mean? Above the cone, here, phi is pi over 3. Pi over 3 is just, in this case, it's just phi is going to be pi over 3. Okay, and the sphere is just rho equals 1. It's another rho equals 1, another sphere. Okay, so I believe this is just a box. Okay, theta is definitely between 0 and pi. No restriction means there is a restriction here. Usual restriction between 0 and 2 pi. So below the sphere means rho is less than 1. Okay, yeah, rho is less than 1. You know where this goes. Rho is between 0 and 1, and the phi is above. Above means this one, not sorry. Phi is between 0 and pi originally. So above means I'm talking about this piece, not the one at the bottom. Okay, so this is a piece we are talking about. Okay, in the pre-image, in the spherical coordinate system. Okay, now if you really want to draw the picture here, how do I do that? Below the sphere, so this is a sphere. Okay. Okay, the cone. How do I describe a cone? When phi is fixed, you get a cone. Okay, you get a cone. So you're talking about the region. Rho is less than or equal to 1. Okay, and the phi is actually above the cone. So phi is, yeah. So to describe the region is actually the rho is between 1 greater than 0. Phi is greater than pi over 3, less than pi. Okay. Oh, sorry. Phi, no, because we start from there, 0 here. So actually, if you look at the picture, it's clear that phi is between 0 and pi over 3. Okay. Yeah, that's right. So this is phi. You know, phi equals pi would be the source pole. Okay. Phi equals 0 is the north pole. Okay. No. Oops. That is the opposite way. Yeah, if you, yeah, then sorry, this is the wrong picture here. Yeah, it's actually below the box. That's what my origin was correct. Okay, I thought it's on the top of the sphere. That's why it should be on. So this is a pi over 3. Okay, yeah, that's correct picture. Phi is between 0 and pi over 3. Okay, yeah. If you look at the picture here, it's clear, right? Phi is it's above the cone, so phi should be less than pi over 3, and it's below the sphere. It's inside the sphere. In other words, then rho is between 0 and 1. Right. So that is a picture. Right. So corresponding per image will be the box like that. Okay. So that's it. Then you have the map here, right? And don't forget this mapping, right? You probably don't need to even write down that, but let's keep it writing. Okay. This is our. Okay. This is the map. Right. For given rho theta phi, you get a point in the XYZ plane, space, XYZ space. Okay, so what is our triple integral? Triple integral, this is my E, okay? This is my E bar, okay? So triple integral over the E, it's a y square and the z square and dv can be changed to the triple integral of E bar, okay? And y is, you see, I still need a y, right? Y is z squared. Y and the z. I have to replace that. To save time, maybe I still should put it here. So y times z is a rho square, and the sine phi, cosine phi, sine theta, and the square, right? And remember, dv becomes dv bar, but there's an addition term, rho square, sine phi, right? And the dv bar. This is from the Jacobi. Right? I already mentioned that earlier. Yeah, this is from the derivative of the map. Okay, the derivative of the map. We have to have addition term. Don't forget that part. So that is a triple integral over E bar, but then the E bar is 9, so it's a box. Right, that's a good part. E bar is 9, so it's a box. Okay, so I can express that the iterated integral quickly. So let me simplify this a little bit first before we move on. Okay, so I have a rho square and square, so the fourth pound, and rho to the sixth pound. Okay, and I have a sine phi squared and sine cube phi cosine phi. Wow, sine square theta. And then dv. I think this will be the triple integral. It's pretty separate. They're all separate, right? So I can get, yeah, the rho is from 0 to 1, right? Rho is from 0 to 1. Right? 0. Theta is from 0 to 2 pi d theta. The phi, be careful, from 0 to pi over 3. Okay? So I get all those okay, but you can this is a d phi. Okay, so it's a part. No space left. But when you evaluate this integral, you just need to focus on phi. Then you take it out. Actually, quickly can realize that this is a product of 3 integrals from 0 to pi over 3, sine cube of phi, and cosine square phi d phi. And this integral from 0 to 3, sine square theta d theta. Then this integral from 0 to 1, rho to the power 6 d rho. Okay, so you can evaluate each of them. Yeah, you know, you can take it out step by step. But yeah, it's not a. I'm not going to complete the this integral. Just leave like that. Okay. So the only problem is how to evaluate the integral of this. How to evaluate the integral of this. I'll give you some hint. Okay. So sine square theta is going to be 1 minus cosine 2 theta divided by 2. Okay, you have to use that formula to evaluate this. But how about sine cube phi and the cosine square phi? This will be difficult, right? Maybe not. Okay. Oh, wait a minute. This should be 2 pi. Okay, it's 2 pi. Yeah. But for the integral of sine cube phi cosine square phi d phi, you have to use substitution. Okay, how do you do that? So you have sine square phi cosine square phi sine phi d phi. Okay, then clearly you can use a substitution. U equals cosine phi. Okay, then du equals negative sine phi d phi. Right, so the integral becomes sine square phi cosine square phi negative du. But how can I change the other part to phi to u? Because sine u squared is 1 plus minus cosine square phi, right? So you will get negative 1 minus u square and u square du. Okay. And you can also change the order, right? 4 minus u squared du, okay? Then find the antiderivative of this. Okay, and then you replace u by cosine phi. So that's it. So yes, you can finish the rest of that. I'm going to trying to discuss a little bit more problems here, how to set up the integral using the spherical coordinates. The next problem will be number 30. Okay. Find the volume of the solid that lies within the sphere. Okay, x squared plus y squared plus z squared equals 4. Then above the xy plane and below the cone, z equals x squared plus y squared. Okay. So let's look at the picture first. You're going to draw the graph. It's a sphere, right? Sphere was radius 2. Right? So sphere was radius 2. Above the xy plane, okay, it's obvious, above the xy plane. Below the cone, how the cone looks like? This is a cone. This is a problem very similar to the above. Okay? But this time, let's describe the region. So we're talking about this part. Okay? Of course, you can find if we can find the volume of the top one, you can use a subtraction, right? You know, minus the volume is a semi-sphere, semi-ball, but minus the volume is a cone. Okay, that probably is a difficult level same, so why not just find it directly? So use the polar coordinates, use the spherical coordinates. Let's set up the integrals. This is a E, right? and I want to find the corresponding simple region. Okay, the map is still this map. I equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. Okay, so we have to determine the pre-image of that solid. Okay, and then transfer the integral. You see, the volume is just as a triple integral of E of dV, right? At constant 1. The volume of the constant 1 over that E gives the volume. So E itself, the region is harder to describe. Okay. Now, if you use a polar, you use a sphere coordinates, it'll be much easier. If you don't use a sphere coordinate, I still can set up an integral. Okay, but it's not easy. I will show you how to do that. Okay, just set up an integral. Okay, iterate the integral. I can do that. But you probably still have to use the polar coordinates to evaluate the double integral. Okay, but right now, okay, how do I describe this? I want to change it to dv is roughly speaking dx dy dz. I want to find the region here and the E bar, right? And the volume form will be d rho, d theta, d phi. Okay. I needed to find that one. The pre-image of this region. Okay, how do I do that? I take an aperture point inside this solid, and I draw the line from the region. And then I look at the phi. I think phi is between pi over 4 and pi over 4 and pi over 2. Why? I think pi over 2 is easier to see because it starts from the xy plane. Why it's going to be pi over 4? Then you just look at the cross section between the cross section of this solid with the YZ plane. Okay, you can determine the you can determine the angle. Okay, so let's look at the solid. This is a YZ plane. Okay, and over there, this equation will be z equals, because x equals 0, so z equals y, right? So z equals y, of course, this is a pi over 4, here's a pi over 4. Okay, this angle. Okay, so that's why phi is between pi over 4 and, okay, yeah. So the cross section, the intersection of the solid with the YZ plane, okay, is going to be this portion. This is a portion in the YZ plane, right? So the phi is between pi over 4 and pi over 2. Yeah. Okay. That's it. So now I'm going to describe the corresponding picture here. Phi, this radius is 2. Oops, 2. Okay. And theta is no restriction on theta. It's 2 pi. So I draw this line, okay? But phi is between pi over 4 and 2 pi. So this is a pi over 2 and the pi over 4. So how can I describe it? It's a little bit harder to draw it. Yeah, this is a pi. I'm pretty sure, yeah. Because phi is between pi over 4 and pi over 2. Yeah. Okay. this piece is mapped to that solid. Okay. It's not necessarily 1-to-1, but along the boundary, maybe not 1-to-1, but the interior is 1-to-1. Okay, there's unique correspondence. All right, so now this is going to be what is a dv becomes? Dv becomes something dv bar. Actually, this should be rho square sine phi dv bar. Okay. And the E is described by that. E is between, rho is between 0 and 2, theta is between 0 and pi, 2 pi. Phi is between 0, pi over 4 and pi over 2. So I can write down the integral directly. I can put a 0 outside, okay? Then theta from 0 to 2 pi d theta, right? Then and phi is pi over 4 and pi over 2 and rho square sine phi d phi. Okay. To save space, I don't put brackets over there. All right. So now, let's evaluate. Right. Let's evaluate. So the integral of cosine. Cosine phi is negative, the antiderivative of cosine, sine phi is going to be negative cosine phi. Evaluate the two end points. And cosine pi over 2 is going to be 0 anyway. So minus pi, so that is going to be rho square 2 over 2, okay? And then the next integral is independent of theta, so I get 2 pi. So I get 2 pi times square root 2 over 2 is going to be pi square root 2 rho square. Yeah. Then the antiderivative of this is rho cube. Okay. So the answer is 8. 8 square root 2 pi divided by 3. So that is the volume. Okay. So the key idea is to determine the pre-image of that region. Now, if you don't want to use a spherical coordinate, can you work on that directly? Right? This is a sphere. This is a cone, right? And the surface is z equals. Oops, what is? Let's go. Okay, it's going to be square root of x squared plus y squared, right? The cone is described as the equation, and this is going to be 2. How can I set up integral for this this volume? Okay. Well, there was a little bit problem here. Okay. So what I'm going to do is I have to have a 2. You can break into 2 integrals. Okay. So this is a d. Okay. D is going to be xy, x squared plus y squared less than equal to 2 squared. Okay. So that's in the xy plane. That's one way to choose, right? And there's another circle here. If this is a red circle, and I have to determine this circle. What is the radius of that circle? Yeah, what is the equation for that circle? Yeah, for that circle, z is x squared plus y squared, z squared, right? But the whole sphere, you see, here is going to be x squared plus y squared plus z squared equals 4, right? Right? So now z squared is going to be x squared plus y squared. So that one is x squared plus y squared equals 2, I think. Yeah. Okay, 2 squared plus, yeah, 2 plus 2 is equal to 4. Okay. So the radius of that circle is a square root 2. Okay, that's it. And now we're going to set up the integral. Okay. What I'm going to do is this triple integral can be use this iterative integral. Okay. Iterative integral, then you have to determine the z for every point in the, so this is from 0, no problem. The question is, what is the upper limit for the z? Then it depends on where the point. If inside this red circle, then use then z's upper bound will be square of x squared plus y squared. But if it's outside the red circle, then it will be different. Okay. So what I'm going to do is I'm going to separate this d into two parts. The first part I simply described x squared plus y squared is less than or equal to 2. In that case, the integral is from 0 to square root of x squared plus y squared dz. Okay. Then for x between 2 and 4 for this one, then z is actually, you have to use a sphere, not as a cone, to get the upper bound. The sphere is 4 minus x squared plus minus y squared. So this is the different part. Then you can use a polar coordinate to evaluate these two double integrals. You get the same result. I just said it's sometimes you still can use as a method to solve it. Okay, so this you will get square root x squared plus y squared dA, another double integrals, and this will be square root of 4 minus x squared minus y squared dA. Okay, slightly different, but if you use a polar coordinate, you can evaluate without any problem, and you get the same result. If you use a polar coordinate, and this will be from 0 to square root 2, and then this from 0 to 2 pi, and here's r, and then have another r, and d, dr, d theta, the first one, I just write down this. Okay, and here I get square root 2 and to 2, and from 0 to 2 pi, and here 4 minus r squared, r, dr, d theta. Okay, so not too bad. Even the second one, you can use a substitution to evaluate. Yeah, you can evaluate. You will get same result that we got here. You see, but it will be much complicated if you don't use strict coordinates. Okay, there are almost no time. Let me almost no time. So, but there's another way to also use the iterative integrals instead of using the. Okay, this is a cone, right? You can go in this way. You choose a z first, then you determine each disk. As this is a z. You determine each disk in the space. Okay, so that's called the corresponding image here is called dz. Then this triple integral is going to be Is going to be z is between 0 and the highest point. Yeah, figured out what is a z. Okay, so it's going to be integral dz. Then you have a double integral, but you have to determine by the value of z and the dA. Okay, that's another way to determine to evaluate this triple integral. Okay, so what is the highest value for the z? Because this is the equation x squared plus y squared plus z squared equals 4, right? And the top one here, the intersection z squared equals x squared plus y squared. So so what is the value for this? It's going to be z squared equals 2. So z is the square root of 2. That's the upper bound. Here's the square root of 2. Okay. So that's the square root of 2. Then, yeah, much simpler. Then you find the, then what you're going to do is you find the area of that disk. Okay. All you have to do is determine the radius of that disk. Okay. And that can be for any fixed z. It's easy to find out because x squared plus y squared equals 4 minus z squared. Right? So the radius square is going to be 4 minus z squared. So it's going to be pi r squared 4 minus z squared dz. Okay. It's not too bad. That's another way to do the problem. Okay. Then you simplify it. So I'm stopping here. You can do the rest of that.